This is the Chapter 14, Lipid Metabolism Commentary. In this commentary, we're going to be talking about lipid metabolism. So we're going to be talking about some of the pathways for catabolizing, breaking down lipids to release energy, as well as building up lipids in order to store long-term, aka in the form of triglycerides. So, quick overview, lipids are stored in large quantities and they have a lot of energy. If carbohydrates are the quick burn, kind of like gasoline, lipids are a lot like wood, where it's very slow burning, but there's a lot of stored energy. So it's almost like burning wood. So they're very slow burning biomolecules. With a lot of stored energy, and we're looking at 9 big capital C calories per grams, or kcals, 1,000 calories of energy per gram. So this is roughly twice the amount of energy released from carbohydrates or proteins. So we like to use lipids as the last straw energy biomolecule if we're going to be starving for long periods of time. So in the U.S., you have enough fat on your body to allow you to exist anywhere from 30 to 40 days. So let's go ahead and focus on breaking down lipids. When you first eat any food that contains fat, and we're going to be focusing on triglycerides in these examples. The triglycerides are digested and broken down via enzymes, acid in your stomach, into smaller monoglycerides, fatty acids, and glycerol. They're then absorbed through the intestinal mucosa cells, and they're then actually encapsulated. So if I have triglycerides, if I have my cholesterol, and I'll use TG for triglycerides, CE for cholesterol, they're actually encapsulated in a structure called a chylomicron. Chylomicrons are actually a combination of proteins and lipids, and they're used to actually transport the encapsulated triglycerides and cholesterol throughout the body. The reason for this is, keep in mind, triglycerides are nonpolar. And basically your body is very aqueous, so it needs to be able to transfer through the body without actually clumping together in a micelle, which is a bad thing. So the chylomicrons, these are what we learned earlier, lipoproteins, because they're a combination of proteins and lipids, and they transfer the encapsulated triglycerides, cholesterol, glycerol into the lymph system, at which point they're transferred into the blood and finally to the liver for future biochemical packaging. So let's go ahead and quickly go through this. The chylomicrons, along with the monoglycerides, fatty acids, cholesterol, whatever inside the chylomicron, they're going to go ahead and travel to the liver, and then they're going to be modified within the liver. So if you're curious, this is roughly what a chylomicron looks like. Here we see it's a combination of protein and lipids, and inside we have our cholesterol and triglyceride. Now, let me say this last part again. The chylomicrons containing the triglycerides, cholesterol, are traveling to the liver, in which case they're going to be modified. So, everything is going to be modified. The cholesterol, the triglycerides, and more importantly, even the chylomicron is going to be modified itself. The capsule which contains everything. I'm going to go ahead and focus on the capsule itself at this point. That's going to be modified. So the chylomicron is going to be modified, and its structure is going to either form HDL or LDL. HDL stands for a high-density lipoprotein. LDL stands for a low-density lipoprotein. The density refers to the amount of protein present. So, and in general, proteins are any type of protein is more dense than its lipid counterpart. So consequently, the more dense the structure is, the more protein it has. Let me say that again. The more dense the structure is, the more protein it has in its container sheath. So high-density lipoproteins contain more protein than low-density lipoproteins. So keep that in mind. Summarizing this right here, let's go ahead and go to the next step. We've automatically assumed that one lipoprotein transport container is better than the other. So the good lipoprotein is the high-density lipoprotein, the one made up mostly of protein. The bad one is the low-density lipoprotein, whose outer sheath or container is made up more of, whose outer sheath is made up more of cholesterol, phosphoglycerides, rather than protein. So, why is one bad and why is the other one good? Well, it turns out, let's go ahead and focus on the bad one first. Again, the body thinks it's living in the caveman days. It knows it needs a constant fresh supply of cholesterol because cholesterol is important in helping to make cellular membranes, hormones, so forth. So, assuming that the low-density lipoproteins is a major transporter of cholesterol, it needs to be able to transport it and give it to the parts of the body that needs it. Now, there are many times when it doesn't need it, so what the body does is it literally double parks along the side of the artery. So if we take a look at this picture right here, here is an artery, and what happens is these low-density lipoproteins, when they're not transporting cholesterol to a particular part of the body, they literally will double park and wait until they're called upon. Now, in our nation of excess, where we have too much cholesterol, triglycerides in our diet, what happens is our body doesn't know the difference, and it thinks more the merrier. So it will actually increase the amount of low-density lipoproteins it has present. These low-density lipoproteins will instinctively double park along the sides of the artery, waiting to be used, not knowing that there's already too much to begin with. So think of trucks, where there's too many trucks on the freeway and they're double parked along the sides of the freeway. After a while, if they were to continuously double park, they would start to block the freeway, and which is exactly what happens to the artery. They start to block the artery, and then you start to have this accumulation, which eventually turns into what we call atherosclerotic plaque, or plaque buildup, which is the determining factor for atherosclerosis. Notice I can't have trouble saying the word atherosclerosis, so take my word for it. So that's why it's the bad stuff. Keep in mind, it's only bad because we basically eat too much fat or cholesterol, and the body doesn't know the difference. If we were to live in apocalyptic times, caveman days, then these really wouldn't be considered bad. Let's go in our day and age to the good. The good HDL we consider good because they help regulate the LDL storage. They literally will come upon a low-density lipoprotein, and they will basically hijack all of its stored cholesterol, triglyceride, and then transport it. So it helps regulate the LDL storage. So the more of the HDL we have traveling through our arteries, the more likely the empty HDLs will come along a LDL and steal its cargo. So they help regulate the LDL storage. More importantly, the HDLs don't sit there and double park. What they actually do is they will actually go and empty into the bile, at which point they then empty into the intestine, and using this guy as a gross picture, they then are, yes, excreted. So the good thing about HDLs is the cargo from the LDL is removed and emptied from the body. So it's emptied out of the bloodstream via the bile ducts into the intestine and then finally excreted out the body. That's why it's good, at least in our nation of excess. Let's keep going. The body prioritizes carbohydrates and glycogen use. So basically, the brain needs fresh amounts of carbohydrate. The minute you start starving, automatically the brain will start hoarding the leftover carbohydrate, so that way it could store it for the brain. It also likes to store it for the heart as well. And it will sit there and also store it for blood cells as well. So it prioritizes the leftover carbohydrates when the body starts to starve. Parts where it doesn't consider important for low amounts of carbs is the muscles. So that's one of the reasons you feel weak if you haven't been eating. The liver also has a low priority. Now, what then happens is triglycerides are stored in the adipose tissue and mobilized by the hormones. So as you start to starve, basically hormones set free your adipose tissue fat cells. Release the triglycerides from the adipose tissue fat cells. So the fat cells don't move, it's the triglycerides from these fat cells. Now, normally the body has its own separate supply of triglycerides, which it uses for energy. But when you start to starve, that's when it starts taking the triglycerides from the actual fat cells. There's only another time that it actually takes the triglycerides from these fat cells, and that's when you're exercising. So I know it's two extremes, either exercising or starvation, but that's how you get rid of the fat from those pesky fat cells that everybody wants to lose. Going back to the hormones stimulate the release of the triglycerides, which we call fat mobilization. So it basically releases the triglycerides, and these are broken down into fatty acids and glycerol, which then enter the bloodstream. Now, again, these are nonpolar, so they need some way of being, or they're roughly nonpolar, so they need some way of being transferred. So they're transferred through a complex with serum albumin, which is a protein, and are transported to the desired cells in the body. I need to go ahead and break down glycerol and triglycerides. Please do not read any more into what I have written here. Yes, it's a ton more complicated, but these are the highlights that you absolutely need to have on your cheat sheet. Yes, it gets more complicated. Yes, this is hard because I can't give you the overall big picture because there are so many other things going on. So try to focus on what I have here, and let's go ahead and move on. Be sure to put it in your cheat sheet. Let's go ahead and focus on glycerol. This is one of the things that are released during fat mobilization. Notice this is a piece of triglyceride where the glyceride head was taken off, forming glycerol. Glycerol is broken down for energy. The first thing, however, that happens is it needs to be, and this can be very difficult, it needs to be energized. So let's go back to our little energy hill. Here is glycerol. Yes, there is a nice amount of energy that needs to be released, but notice it's stuck on the side and it needs to be pushed over the energy hill. So An available ATP provides the initial energy in order to energize it to push it down the energy hill. Once it's in this form, glycerol 3-phosphate, the NAD comes down by and takes off 2 hydrogens, one here and one here, forming a nice ketone. We call this dihydroxyacetone phosphate. In the process, it regenerates an NAD to NADGH, which earlier we talked about how this powers the electron transport chain oxidative phosphorylation for producing later ATP. Let's keep going. It doesn't stop there. This can then be inserted into the glycolysis chain, which can then be broken down into pyruvate. Now, if you're starving, there's 2 things the body may do. It may either use the pyruvate and immediately release the energy, or if it starts to run low on glucose, because keep in mind the body's brain, blood cells, even your heart, it needs fresh supplies of glucose. It may actually make new glucose and then go ahead and store it to the brain or to your heart or to your blood cells and provide energy. So it either releases it right away or it stores it temporarily in the form of glucose for whatever part of the body needs it. When it converts it from pyruvate to glucose, we call this gluconeogenesis. Gluco for brand new glucose, hence the term gluconeo, and you can figure out you're making brand new glucose by the name genesis.